In this video, I'm going to talk about Bernoulli Principle and Coanda Effect, which are important in terms of lift formation in aircraft's wind turbines. Assume that aircraft is just flying this direction and wind is in opposite direction. If we assume that we don't have engine here, the wind tends to push backward the airplane, and this is why we get here drag force. And engine generate thrust in order to overcome this drag force induced by wind. And the weight of airplane here is also overcome by the lift generated using the wings of the aircraft. If I take a cross section of the wing, I get something like this. The cross sections geometrically looks like this. This element is called airfoil, which is the main responsible element to generate lift in the wing. This point of the airfoil is called leading edge. This point is called trailing edge. If I connect them together, I get a curve called chord. Airfoil has designed in the way that in the bottom of airfoil we get a high pressure system, and on top of that we get low pressure system. And we know that the airflow from high pressure to low pressure area. And this is why the lift upward movements just is formed in airfoil. And also the length of top side of the airfoil is more than the length of the bottom side. There are different types of airfoils, asymmetric type as I shown here, or symmetric type, depending on the application. In this figure you see different types of airfoils. They are mainly asymmetric, and also here you see one somewhat symmetric kind of airfoils. Let's look at the horizontal wind turbines containing 3 blades, 1 rotor. The whole system is supported by tower and is bottom fixed. And also in the floating turbine, offshore wind turbine case, it anchored to the bottom through the mooring lines. If I take a look on one blade here, you see the blade looks like this. And if I take again cross section along the blade from the rotor side, because here we have a rotor, towards the tip area, we get different shapes and sizes of the airfoil here. But there is another kind of distinguished characteristic here. The blade is also twisted towards the tip area. Let's focus on Bernoulli Principle. Bernoulli Principle is going to bridge between the velocity and pressure. And like the conservation of energy, it says that the total amount of the pressure remains constant in tube flow, as shown here. We have a tube with different cross-sectional area here, and here different area, here different area, at different heights. Here, for this point, the height is h1. For this point, for example, the height is h2. We have 3 types of pressure here. According to the Bernoulli Principle, this sum remain constant. V is the velocity of flow. For example, here at point 1 we have V1, at point 2 we have V2. And we know that V2 is greater than V1. And this principle, if we apply for point 1 and 2, in the absence of the hydrostatic pressure, for the sake of simplicity, looks like this. Here we assume the incompressible flow so that the density rho remain constant. And it says that if the velocity increase, then the pressure have to decrease. The next effect is called Coanda effect. Assume that we have free falling stream of water and we have a spoon which is allowed to move freely through these pivots. If we let the spoon to touch the water stream here, then the water stream start to follow the curvy surface of a spoon like this, and it will not deviate that way. This effect in which the flow field remain in close attachment with the solid surface which it encountered is called Coanda effect. Assume that we have a ball and we have a candle also. If we have a flow of air or wind here, according to Coanda effect, it follows the surface and it may affect the candle light here. The reason is that we have this ball and then flow of air, just see this guy as an obstacle. It just deviates like this. However, it pull away the air parcels at the surface, close to the surface, and then generate low pressure system very close to the surface of this ball. And also we have high pressure static pressure around, which cause this streamline return back towards the surface and remain attached to the surface. And in airfoil example also we can see how it presented. Assume that we have wind here, it's remain close to the surface, and here I'm using a streamline lines. I assume that my flow is steady state, incompressible, and therefore all kind of air parcels have very well organized pathways. It means that they passes an organized trajectory which called a streamline. Different streamline will not also cross each other. And as I mentioned, the airfoil has designed so that it generates high pressure system here and low pressure system on top of the airfoil. According to the Bernoulli Principle, I can think of this part as a tube flow, which I have different cross-sectional area at different height here. I know that if the velocity is v, here the velocity increase, and at the same time, according to the Bernoulli Principle as stated here, then the pressure should decline here. And therefore here we get pressure, low pressure system. And pressure distribution along this top area of chord also changes. If we sum up all kind of the pressure distribution along the top side of chord, we see that there is a point which this force can act on the airfoil, and this point is called center of pressure. This point is close to the, depending on the angle of attack, is close to the leading edge. Angle of attack is the angle between the chord and the wind direction here.